All guests have been muted. You can unmute your line by pressing *6.
Laura?
Yes.
Okay, yay. Okay.
Right. All these little different things I have to remember to push.
So we're going to go back to mute till 2 o'clock, and then after Erica introduces you, you come back on.
Okay, so should I mute now?
Yes, that's it.
Okay, I will mute, and then after the introduction, I'll unmute.
Yes, yep, that's it. Okay, bye.
Hello, everyone. This is Erica Spotts at OBSSR, and I would like to welcome everyone to the second webinar in our Advances in G/E Research in the Behavioral and Social Sciences webinar series. This series emerged from meetings of the Gene Environment Planning Committee at the NIH as a way to educate both the NIH and the research communities on emerging issues and advancements in G/E research in the behavioral and social sciences. We're beginning the series with data harmonization and pooling, with the requirements for larger and larger sample sizes for adequately powered G/E research in all scientific areas. There is an accompanying need for pooling and harmonization of relevant data, and we wanted to get different perspectives on how that might occur. Today we have Dr. Laura Jane Barout presenting her webinar on harnessing precision medicine to reduce smoking. She is the alumni endowed professor of psychiatry at Washington University School of Medicine in St. Louis. She graduated from Harvard Radcliffe College with a bachelor's degree in biochemistry and molecular biology, and she earned her medical degree from Washington University School of Medicine and then completed her residency in psychiatry there as well. She then spent 1 year as a postdoc research fellow at the Karolinska Institute in Stockholm, Sweden. Dr. Barout has built a successful research program devoted to understanding the genetics of substance dependence, and I will now let her speak about some of that work this afternoon. Welcome, Dr. Barout.
Thank you very much for inviting me to speak today and for this opportunity to talk about some of the work that I do and my thoughts about how my group, at least, is moving forward studying gene and environment interactions. So when I kind of am thinking about the genetics and environment, I think of kind of these main areas. My talk is going to go through these different chapters. The first 4 have to do with my view of genetics, then how genetic variation drives smoking behavior, how the genetics of smoking actually relates to the genetics of lung cancer and other diseases, and then pull this back into smoking cessation, which really is our ultimate goal of understanding the genetics of smoking behavior. And then I'm going to end with my general thoughts on what the lessons learned are going forward. So, the brave new genetic world. I view genetics as the modern genetics era as starting in 2005 when we completed the human genome. And right away there were these questions about, was the human genome project really worth the effort? It was very expensive, and almost immediately the genetic variation for age-related macular degeneration, a strong genetic risk factor that explains a lot of the development of this disease, was identified. And NHGRI has this genome-wide association catalog, and what you have here is the visual of all the chromosomes. And in 2005, we just have that one little marker on chromosome 1. But by 2006, more variants had been identified. And if we go through 2007, 2008, 2009, 2010, 2011, 2012, we really see that things have moved forward quite quickly with the identification of many variants associated with a variety of different illnesses. And this has just continued, though we really can't even update the chromosomes now, just because we've identified so many different common genetic variants associated with complex diseases, as well as Mendelian diseases. So my work focuses on smoking behavior, and genetic variation drives smoking behavior. We've known this for a long time by examining the clustering of different types of smoking behaviors within families. Twin studies and adoption studies really gave us the knowledge that there was a genetic underpinning to it. And so this has been an area of research of mine and several others in the field. So the way that we look at nicotine dependence is that there's this transition of different types of behaviors across a person's lifetime. You start with never use, and then you move to the initiation of smoking your first cigarette, having the first puff and then the first full cigarette. Individuals then transition from this initiation stage into the development as a smoker, and a smoker is defined as smoking 100 cigarettes in your lifetime. And then some individuals transition to nicotine dependence. So as we view smoking behaviors, environment plays a very strong role in the initiation and the transition to becoming a smoker. Cost is a very important driver of this. Availability of cigarettes is a very important driver, and we know we've used cost and availability, we've reduced that, and by doing that environmental change, we've really driven down smoking in teenagers quite effectively. But once you become a smoker, defined as smoking 100 cigarettes in your lifetime, this transition to nicotine dependence is actually driven quite strongly by how one responds to the nicotine. And it's essentially we should think of this as a pharmacogenetic response. So as I think of nicotine dependence, this is the brief instrument that is generally used to define nicotine dependence. And two questions really stand out in this Fagerstrom test for nicotine dependence. The first one is, how soon after you wake up do you smoke your first cigarette? Those who are heavily addicted will initiate smoking immediately after they get up. The description is they sit up at the side of the bed, their cigarettes are right there on their bedside table, and they smoke right away. And there's this gradient of how soon after you wake up, with the less addicted individuals waiting a longer period of time. The other question, which really marks nicotine dependence and this inability to quit smoking, is how many cigarettes you smoke per day. And again, there is this gradient of heaviness of smoking. So my group screened over 50,000 individuals in the St. Louis community and Detroit community in the early 2000s. We screened individuals who are aged 25 to 44 years of age, and we queried their smoking behavior to understand these different transitions and then to recruit subjects for genetic studies. So just about 50% of the population in that age range reported initiating smoking, so that they had smoked a cigarette in their lifetime. So I view this as a tremendous success. Half the population had not even smoked one cigarette. Of those who had smoked one cigarette, 58% had transitioned to becoming a smoker, defined as smoking at least 100 cigarettes in their lifetime. And then we could look at the different transitions of smoking behaviors that individuals had. So 19% reported no symptoms of nicotine dependence. These are individuals who never smoked more than 10 cigarettes a day, could delay smoking in the morning, never had any difficulty quitting. A group that's often called the chippers. These are often the individuals who report behaviors such as, oh, I just smoke a cigarette or two after dinner. They frequently go for long periods of time without smoking. 35% have some symptoms of nicotine dependence, and then just over 44% are nicotine dependent. So these are heavy smokers, individuals who have difficulty quitting, individuals who have difficulty refraining from smoking, and they smoke right after waking up. So if we think about this, again, not every smoker is nicotine dependent, but about 80% of individuals have some symptoms or are nicotine dependent, and then there's this less common group of individuals who are able to kind of take it or leave it with their smoking behavior. So we recruited from these two extremes of nicotine dependence and non-nicotine dependence and no symptoms for our genetic studies. So we published the first large-scale genome-wide study of nicotine dependence, and we identified variants in the chromosome 15 region associated with nicotine dependence. This was quickly confirmed in multiple large-scale studies from other groups, and really kind of driven home with these even further large-scale consortia of over 80,000 smokers. So this slide is from the TAG Consortium, and it represents a Manhattan plot. So a plot of genetic findings for heaviness of smoking. So the x-axis represents the different chromosomes. The y-axis represents the negative log of the p-value. So the higher the peak, the higher that number, represents the strength of the genetic finding. So as you could see, there is a hot, striking peak on chromosome 15. When you look at cigarettes per day, which is the proxy for nicotine dependence, which is available in many large-scale studies, and this region contains the absolute strongest genetic risk factor for heaviness of smoking. So underneath this peak on chromosome 15 is actually a cluster of nicotinic receptor subunit genes, the alpha-5, alpha-3, beta-4 nicotine receptor subcluster. We have subsequently pushed this forward and demonstrated that there is an amino acid change occurring in the alpha-5 nicotinic receptor that is driving part of this behavior. There's a second biologic mechanism with an alteration of how the alpha-5 nicotinic receptor is expressed. It's mRNA. And there's also less common variants and rare variants that are independently contributing to the development of nicotine dependence. So I've just kind of very quickly summarized about 5 years of work showing that there's this very strong genetic finding for heaviness of smoking. And now the question is, what does this mean? Who cares? How do we move this forward? So at the kind of parallel to our work with smoking, there has also been studies of lung cancer and other smoking-related diseases, particularly chronic obstructive pulmonary disease. And if we look at cigarette usage in the United States, we were able to have an estimate of the per capita cigarette consumption based on taxation. And we could see that cigarette smoking is really a 20th century behavior. At the turn of the 20th century, beginning in the 1900s, there was actually very little smoking in the population. We had the development of the tobacco industry, the development of mechanized options of making cigarettes, the mass production, and we see in the early 19-teens all the way through the 50s, there was this increase in smoking across the United States. 1964 represents the first Surgeon General report, and that's where we had the peak of per capita smoking cigarette consumption. And it took about 20 years before we really started decreasing smoking in the United States with Clean Indoor Air Acts, and really this change from having every place be a smoking area to every place being a non-smoking area, and this restriction of the availability of cigarettes. We could overlay this graph with lung cancer rates in the United States. So this is lung cancer death rates, and you see that there's about a 20 to 30 year lag of death from smoking, from lung cancer, with the per capita cigarette consumption. And we anticipate that there's going to be a continuing reduction of lung cancer death rate, in large part driven by the decrease in smoking that we've had. So this really, the decrease in smoking represents one of the most important public health successes of the 20th century. So as we were doing our genetic studies of smoking, 3 large-scale genetic studies of lung cancer came out and identified this same chromosome 15 peak as the strongest association for lung cancer. This was followed up with a large meta-analysis of almost 15,000 lung cancer cases and almost 30,000 control subjects. And you can see this Manhattan plot mirrors in a large part the Manhattan plot that we have for smoking. We have this extremely strong peak on chromosome 15, which underlying it is the nicotinic receptor genes. So what we know now is that multiple behaviors drive lung cancer with smoking, and this risk is associated with the alpha-5 nicotinic receptor. This variation in this receptor drives how many cigarettes you smoke per day. It also drives how deeply one inhales each cigarette. So the idea is that if someone reports that they smoke 20 cigarettes per day, not everyone who smokes 20 cigarettes per day smokes their cigarette the same way. Some people inhale each cigarette very deeply, and by studying biomarkers, we've now shown that this variant is influencing both how many cigarettes you smoke and how deeply you're inhaling each cigarette. So, which we believe is all related to how an individual is titrating their dose of nicotine. So, moving forward, really the ultimate goal is smoking cessation. And what we want to do is understand what the biology of smoking cessation to see if we could improve the ability of people to quit. So if we think of our model again of nicotine dependence, we have individuals who are nicotine dependent, and how do they transition from being nicotine dependent to successful cessation and remission? And what are the biologic factors and environmental factors that are driving this step? So interestingly, as we found this incredibly strong genetic driver for heaviness of smoking and how deeply you inhale each cigarette, the first publication that came out and looked at these alpha-5, alpha-3, and beta-4 nicotinic receptor genes found no relevant influence on smoking cessation. This was a large-scale study of older people who, some who had quit and some who had not quit in the population. The TAG consortium also did a looked at smoking cessation. They defined smoking cessation as successfully quit for 2 years. The Manhattan plot on the left is the one that I had shown you previously. I actually took the Manhattan plot on the right and squished it down so that the scale was actually the same, that went up to 10. And as you can see, there is no peak anywhere near as strong as the genetic influence on heaviness of smoking. So even though we have this strong driver of heaviness of smoking, nicotine dependence, even though we know that how dependent you are predicts very strongly your ability to quit, we were not seeing the genetic influences really transition to successful smoking cessation. Until this paper came out, which I often just call the pregnant lady study. So this is an interesting paper that came out of the UK and was following up the LSPAC study, so a longitudinal study that followed women who were pregnant and their children. So one of the things that they had done in this study is they, as they were recruiting women who were pregnant, they queried their smoking behavior during their first trimester of pregnancy, and then followed them up to see, did they quit by the third trimester of pregnancy. And what they found is the alpha-5, alpha-3, beta-4 cluster strongly predicted successful or not successful smoking cessation during pregnancy. So I think of this paper as a time when women are pregnant, there's a high environmental drive to quit smoking. Physicians are telling women to quit smoking. Just socially, being pregnant and smoking is not very socially acceptable. And in this study, we do see the genetic influence of this chromosome 15 cluster. We also saw the influence of this chromosome 15 cluster in a smoking cessation trial. So this is a trial, Remission Chen led this work, and Tim Baker and Michael Fiore led this smoking cessation trial from the University of Wisconsin. And I'm going to lead you through a series of slides that show this genotype by treatment interaction. So what we have here is we have 3 haplotypes. They're really equivalent to the genotypes, the same genotypes that were predicting heaviness of smoking. And what you see in this yellow group is a decreased ability to quit smoking when you move from H1, which is the low-risk haplotype, to H3. So individuals, the lower abstinence is lower success rate with smoking cessation. So in the yellow groups, these are individuals who are receiving counseling, but but placebo pharmacologic treatment, so no active pharmacologic treatment. If you look at the groups that are receiving active pharmacologic treatment and counseling, they were receiving nicotine replacement therapy or bupropion or combination. You see that the genetic variation does not predict smoking cessation success. All 3 groups are have the same rate of success for smoking cessation. And when we look at this high-risk group, this is the group that is at highest risk for heaviness of smoking, highest risk for inhaling deeply, highest risk for developing lung cancer, highest risk for developing COPD. This is the group that is responding particularly well to active pharmacologic treatment. This other group, the low-risk group, actually is not receiving really any added benefit in this data set from pharmacologic treatment. And this is an example of a genotype by treatment interaction. The idea that some individuals, the high genetic risk group, is receiving the strongest benefit from pharmacologic treatment. And the low-risk group is really not receiving much benefit at all. So this could be translated into number needed to treat. So this figure here is basically the same data that I've shown you already, but divided out into the placebo group now on the left and treatment on the right. And number needed to treat is this idea of how many individuals do you need to treat to get a benefit for one person. So the perfect number needed to treat is 1, where if you treat one person, that individual has a benefit from treatment. Many, we think of antibiotics for pneumonia, the number needed to treat is often somewhere around 10. If we think of other types of treatment, treatment of hypertension, treatment of cholesterol, the number needed to treat is much higher, 30 or 40. And what we have here is a number needed to treat based on these different genetic variants that ranges from 4 to over 1,000. So the high-risk haplotype H3 is having a very strong response to pharmacologic treatment. For one person to benefit, you only need to treat 4. That's a very good number needed to treat. And the low-risk genetic group, the H1, is essentially receiving no benefit from pharmacologic treatment. This data, we were trying to understand again why some of these larger studies previously demonstrated no success in identifying these genetic variants. And what we think is happening is this kind of subtle delay in smoking cessation. So with time, almost everyone quits smoking. And it's the question of when you quit smoking, almost not if you quit smoking, but when. And so we subsequently have done this survival analysis looking at the age of quitting smoking. And what we find is that there is a 4-year median delay in age of quitting smoking. And this delay in quitting smoking causes about a 2-year loss of life by this 4 years of additional smoking. And we could also look at the age of onset of lung cancer. So lung cancer is a very deadly disease, even with treatment. There is high mortality after 1 year, and almost 90% die after 5 years. And this genetic variant in chromosome 15 in the alpha-5 nicotinic receptor predicts a 4-year earlier age of onset of lung cancer diagnosis. So if you have a lung cancer diagnosis and you have the low-risk genotype, the median age of being diagnosed was 65. Those with the high-risk genetic variants had a median age of diagnosis of 61. So we're having this chromosome 15 region is really driving a lot of different behaviors, and the effect of this behavior is driving diseases, important diseases, lung cancer, chronic obstructive pulmonary disease subsequently. So this variant drives heaviness of smoking, how deeply you inhale, and also smoking cessation success. So where are we moving with this? I'll tell you that the story is a bit more complicated. We have subsequently looked at the data from the Wisconsin Tobacco Research Center, which is on the top. And then we were given access to the Pfizer trial data for varenicline or Chantix. And we looked at these two data sets kind of at the two most effective treatments. So the University of Wisconsin had a combination nicotine replacement therapy, which is felt to be one of the strongest successful pharmacologic treatments. And then varenicline is also one of the strongest smoking cessation treatments. And what we see is nicotine replacement therapy and varenicline increase abstinence across all 3 genotypes. Though there is some difference in the abstinence rate across the 3 genotypes, it was not statistically significant. But there was a significant difference in the placebo arms. So everyone received counseling, and in both of these trials there was a placebo medication arm. And what we see is the University of Wisconsin data on the top shows this transition from low genetic risk to high genetic risk, and less abstinence from that transition. Whereas in the Pfizer data set, we see a completely flat cessation risk across the three different genetic groups. But I want to also highlight what the baseline cessation rate is in these placebo arms, just to kind of keep that in mind. So where do I think we are with this? I think that there's a strong interplay between genes and environment and smoking cessation. When we have a strong environmental push towards smoking cessation, genetic influences could be very strong. So we saw this with the pregnant lady study. So we see the genetic risk when women are pregnant, and the genetic risk predicts who quits and who does not quit during pregnancy. We saw this in the University of Wisconsin smoking cessation trial, which was a very, the subject motivation and the treatment that they were, the counseling treatment, I think was very strong in that trial. They required the subjects who came in to commit to a lot of different follow-ups, so I think it pushed the motivation of the subjects in that trial, and we see the genetics in that trial. We also have seen that the chromosome 15 alpha-5 nicotinic receptor predicts smoking cessation success after you're hospitalized with an acute myocardial infarction. Again, a time when I think it's really driving the idea of, gee, I just had a heart attack, I should quit smoking. But in environments where there's less support for smoking cessation and less, so we could think of this as partner smoking, not as robust counseling, less motivation by the individual, then environmental influences really overwhelm the genetic predispositions, and you no longer see the effect of genetic variation. So that's kind of what I think of as where we are with the interplay between genes and environment with smoking behaviors for smoking cessation and heaviness of smoking. And what are the lessons that I've learned moving forward? I think one of the key things is large samples are needed. So a few years ago, we did these power analyses. This is looking at the power we have for interaction effect sizes, and also the number of samples that we need to detect an interaction. So the slide on the left shows what is our power to detect a gene environment interaction, and we could think of the environment here as a comorbid disorder and the different prevalences of this comorbid disorder. That we really, if we have 2,000 subjects in hand, we really don't start to see, we don't have power unless we're at the prevalence of this environment at about 30%, and we need an interaction effect size somewhere around 2.5 or 3. The reason why I think we saw the interaction with smoking cessation is that we were seeing the interaction effect size was in the range of 3. So that's, we got lucky there. If we look at the figure on the right, this is sample size needed. And again, the prevalence of the comorbid disorder, or you could think of it as, again, prevalence of an environmental influence of 10%, 20%, and 30%. So if you have an E of 10% and an interaction effect size somewhere around 1.5, you're going to need 45,000 subjects to detect it at an alpha of 0.05. If the prevalence is more common, the the sample size you needed goes down, but still any type of interaction effect size under 2, where you need a lot of samples. You need 5,000 samples to get that. The other lesson is what are the important characteristics of your E, the environment. I think it needs to be easily and reliably measured. If it's complex, difficult to measure, takes a long time, then really your dissemination will be limited. So I just put this formula there is how I think of it. We have our, how much it costs to phenotype a subject and how many subjects you could get, and there's always this trade-off that you have. If you do complex measurements, your N is small. If you do simpler measurements, your N is big. And really, this is a decision that you make as an investigator of where you think the money is. Going back to the power slide here, again, these are power for alpha of 0.05. I think you need a sample size of at least 5,000 subjects. And so given that you need at least 5,000 subjects for anything, that means that your phenotyping must be straightforward to measure. And I think we could do that, and I think it has to move forward with, again, how easily is it disseminated into larger groups. I think we also should think about what is the E that we care about. So some E's have very strong effect, and there is likely a gene-environment interaction, but I personally feel some of the E's are less, I'm less interested in certain E's, and I'm more interested in other E's. So in certain environments, I think of child abuse. I really want to reduce child abuse for everyone. There's such a strong main effect for child abuse, so I want to reduce that. And I'm much less interested in understanding that G by E interaction with child abuse. Also, I know I'm going to have less power because child abuse is a less frequent E. Environments where I think variation is much more reasonable and more interesting is the age of onset of substance use. This is how we could increase policy to change the accessibility of substances. So there is a movement now to raise the age for buying cigarettes up to 21. We're introducing marijuana across the country. I think there needs to be some discussion about what age we want people to be smoking marijuana, which is just coming, which is a huge E. That's going to be an interesting change. We could also think of pharmacologic treatment, where I could select different types of medication to treat people with. And again, for smoking cessation, I could think of nicotine replacement therapy, varenicline, bupropion. Similarly, I could think of this for a variety of different diseases. So the pharmacologic treatments, I think, are really important E's for us to go after. I think data sharing is really key. And actually, my group is the first and I believe the only group that had a breach of genetic data. So my data was placed on dbGaP, and a group published early on it. So even though there was this breach of my genetic data, I still think I think it's important to move forward with data sharing. That is really, truly key. So I have lots of people that I work with, both in the United States and around the world, and really I'm just speaking here for my overall group. So with that, I'll open it up to any further discussion.
Thanks for a really great and interesting talk, Laura. Really appreciate it. We have a couple questions in queue, but I would encourage any other listeners to type in their questions in the box on the screen. The first question we have is, are the genetic mutations functional polymorphisms in terms of nicotine metabolism? And I know that this question came in kind of early, so it's probably related to some of the earlier work that you presented.
So everything that I presented has to do with the alpha-5, alpha-3, beta-4 nicotinic receptor gene cluster. There is a similar story with the variants with nicotine metabolism on chromosome 19, but those findings are not quite as strong as the chromosome 15, but there are those two different lines of work. So yes, nicotine metabolism is important, and also for chromosome 15, it's how an individual is responding to nicotine.
Okay. Then I can't read the next question. That's good. The next question is, what is the attributable, all right, now I can't talk. What is the attributable risk for nicotinic receptor mutations for lung cancer and for nicotine dependence? Somehow that seems like maybe something you don't know off the top, you might not know off the top of your head, but maybe it is.
I don't know that off the top of the head, and I generally, I should know it as attributable risk. I think of it as percent of variance explained. So okay. let me tell you the story about the percent of variance explained. If we just look at the one mutation that causes the amino acid change, it explains a little less than 1% of the variance of heaviness of smoking.
Okay.
But even though, what's fascinating is even though that one gene explains less than 1% of the variance of heaviness of smoking, it seems to get magnified over time, and it then explains a 4-year difference in age of onset of lung cancer. And the other aspect about it is we should also think it's explaining how people respond to medications very strongly. So I've become a little bit, I actually think that these numbers of attributable risk or percentage of the variance explained doesn't necessarily carry forward to other aspects.
That makes sense. Thank you for that answer. The third question, with regards to sample size, do you feel meta-analysis and consortia will replace the demands on researchers to obtain these large sample sizes? What about small sample sizes from unique populations?
I think we need meta-analysis. I think we need large samples. I am extremely hesitant about sample sizes less than 1,000 subjects, even if it's a unique population. What I think the genetics has taught us over the years is we need big samples. And I'm even nervous with 1,000 subjects.
Okay.
So now let me kind of step back for a second and say something. I'm talking about common complex diseases. If I'm talking about rare diseases, Mendelian type of diseases, I could get away with small samples. But if I'm talking about complex diseases and behavior, we need large samples. And I think we could collect them. I think we have the ability to do this now. I think we have electronic medical records. We have the ability to do this. This is a complete paradigm change, and it's very difficult for investigators to make this change because so many people have invested in their samples, but we've been, we're blowing it away with the large sample sizes we need and the ability to look at things with large-scale genetics. We're having a paradigm change, and we just have to go through this.
Okay. So the final question that we've got, unless somebody types one in the next couple minutes, thanks to Dr. Beirut from one of our former med students. This is Andrew Zamalzik. Are there any differences in the Pfizer study population that could explain lack of genetic effect in the placebo group?
Could you repeat the question?
Are there any differences in the Pfizer study population that could explain lack of genetic effect in the placebo group?
So let me just go back to this slide where it is. So, so we've been looking at this data. I don't think it's genetic at all. I actually think that the difference in the placebo group is being driven by environment. And counseling is very different between these two groups. So genes and environment make a difference, and the Pfizer counseling was actually more standard counseling that's out there versus the University of Wisconsin teacher trial was really state-of-the-art counseling. The University of Wisconsin teacher, they have 6 counseling sessions, 10 minutes each. They've really tuned into that. It's great. The Pfizer was very brief counseling, and they handed the subjects a pamphlet.
Yeah.
So I think that this is actually a wonderful example of, if the environment here was not as strong, and when the environment was not as strong, we couldn't see the genetics coming out of it. And hi to a WashU student. I was, They
come out from everywhere for these webinars. We haven't gotten any other questions. If there are any last-minute ones, type them quickly. Oh, wait, there is. I would like to use this opportunity. Oh, this is kind of a public service announcement. I would like to use this opportunity to disseminate the PROMIS smoking assessment item banks developed by the RAND Corporation. And then there's a web link. But I think if you probably go to the PROMIS website, anyone who is interested in that could check those measures out. It's free and funded by the NIH. So that's our public service announcement for the day. I don't see anyone else posting any other questions, so I would like to extend a very deep thank you to Dr. Beirut for her great webinar, and for all the listeners who tuned in and asked questions. I thank you as well. I'm not sure when our next webinar will be, but we will keep everyone posted via social media and outreach. So thank you again, and I hope everyone enjoys the rest of their Monday.